Good afternoon and very warm welcome. My name is Dr. Mansoor Nelikal and I'm an enterprise fellow with PSDI, Physical Sciences, Data Infrastructure, and I'll be chairing today's session. If you're new to PSDI, PSDI is a UK-wide initiative building a digital platform to make physical science research data more accessible, reproducible, and easier to share. Today's webinar session is actually part 3 of our webinar series, From Project to Platform, New Resources on PSDI. This series showcases high-quality tools and resources developed through the PSDI 2025 funding call with the aim of introducing them to a broader community and connecting them with potential users. And today's webinar focuses on open repositories for chemistry and energy systems. And we are pleased to have Dr. Josh Bailey and Dr. Hugh O'Connor from Queen's University of Belfast presenting engaging the flow battery community to raise electrochemical testing standards. Dr. Bailey is an Illuminate Fellow at Queen's University Belfast, working at the interface of physical experimentation and computational modeling to improve performance, durability, and sustainability of electrochemical devices. He co-leads international activities aiming to measure and improve reproducibility in flow battery testing while designing new materials and protocols. Our second speaker, Dr. O'Connor, is a postdoctoral research fellow in Bailey's group at Queen's University Belfast, where his research spans electrochemical engineering, reproducibility, low-cost energy storage, and open-source research hardware, with a particular focus on flow batteries. In August 2026, he'll take up a postdoctoral position at MIT in the Brushed group. In today's webinar, Josh and Hugh will discuss the urgent challenges of improving reproducibility in flow battery research and share their insights from large-scale multi-institutional round-robin studies. With that said, I'll now hand over to Josh and Hugh. Thank you.
Thank you very much. Thank you, Mansoor, for the introduction and for all of the organization around this webinar series. So as Mansoor mentioned, my name is Dr. Josh Bailey. I work at Queen's University Belfast, and I'm going to be presenting about our efforts over the last few years to engage the flow battery community to raise electrochemical testing standards. And the sort of latter half of this presentation is really the work that was funded by the PSDI to develop data infrastructures to facilitate these studies. But to kick off, I'd like to start with just saying sort of who are we? So I've introduced myself and Mansoor introduced my postdoc, Hugh O'Connor, but this study is being co-led by MIT, particularly spearheaded by Professor Bouchette, his current PhD student, Thomas Goodwin, and his previous now graduated PhD student, Alex Quinn. Just to kind of cover what it is that I'm going to talk about today, here's just a broad overview. So I will introduce the technology, flow batteries. Some of you will be familiar with these, some of you perhaps are not. I will talk about the specific challenge that we've been trying to address in the flow battery field. Talk to you about the multi-institutional studies that Mansoor mentioned that we've been running internationally for the last few years. And then, as I say, the latter half will be concentrated on the data infrastructure developed during the pilot First Call project from PSDI, as well as the community workshop that their funding supported us putting on. And then finally, some conclusions and future work. So flow batteries. So flow batteries are an energy storage device, and they're typically seen as a long duration energy storage device. So why is it important that we focus on technologies for long duration energy storage? Well, you'll all be familiar with the net zero transition. In the UK, we're legally bound to try to get to net zero emissions by 2050. And a large part of that is generating more electricity using renewables such as solar and wind. But if you look into the detail, the percentage of the energy consumption by fuel type in the UK in 2022 is still quite low for wind, 4.1%, solar 0.7%. This is data from the Department for Energy Security and Net Zero. And part of that is because there are issues associated with this cleaner fuel source. All these fuel sources, I should say. So renewable energy resource challenges tend to be, at least the sort of primary ones, are the unpredictability and the intermittency. So it's not always sunny and the wind isn't always blowing. And there are ways that we can store that. Pumped hydro storage is what tends to be used. And increasingly, we're looking for electrochemical energy storage technologies. But there are some issues with conventional batteries, so lithium-ion batteries, for example. These can be around cost, around degradation once they're installed, the resource scarcity around some of the materials used, and certainly also increasingly something that people are looking at is the safety of these large-scale applications of this type of chemistry. So what exactly is a flow battery? So it's like any other electrochemical device. The cell itself is made up of two half cells. The big difference here versus a traditional sort of lithium-ion battery, say, is that your energy is instead stored not in solid electrodes, but in liquids. And those liquids are stored in external tanks. And we pump those liquids into those two half cells and perform electrochemical reactions. And importantly, and this will be something that we'll be focusing on in later in this presentation, the cell itself is a quite typical electrochemical reactor and therefore has quite a few different components. So it has end plates, often to sort of provide compression and structure, current collectors for allowing electrons to flow in and out. Flow frames, very importantly here, are essentially structures that allow us to control the flow of those liquids through the cell. Porous electrodes, they tend to be carbon papers, carbon felts, carbon cloths. And this is where the electrochemical reactions take place. Gaskets for sealing, and membrane, most importantly, is an integral technology to allow ions to flow, but not allow electrons to go from one half cell to the other. And the general reaction mechanism, like many electrochemical devices, essentially, when you're charging, you've got oxidation happening on one electrode and reduction at the other, and vice versa. And I think the key thing is here is just, again, to situate it versus more traditional technologies, battery technologies. In a flow battery, at least in an aqueous flow battery, you have improved safety. It's much harder to have the flow battery go alight or suffer from sort of thermal runaway processes that you might see in some lithium-ion battery technologies. It's technically more recyclable, so the components are sort of less melded together at the end of life. It's cheaper at larger scale. I mean, this is contentious now with the cheaper and cheaper LFP, but certainly as you scale up, you've got independent scaling of your energy and the size of the tanks versus the power component, which is associated with the stellar stack. So once you get past about 8 hours or so, you can get this improved cost efficiency. And certainly there are some systems out there that have been running for 20, 21, 22 years with very little degradation. So more durable than the 7 to maybe 10 years that you might see typically of lithium-ion battery systems. But there are, of course, challenges. This is an important research field. You've got a less developed supply chain and manufacturing base. They have a lower energy density, more or less inherently because of the nature of energy being stored in liquids. And we have an issue of high component cost, particularly in the membrane, but also if you look at the traditional all vanadium system, the cost is not only rather high, it's also rather volatile. But despite those challenges, I do want to get across this technology is commercialized. Here's an example out in China. There's a 1 gigawatt hour battery. This is the largest flow battery I'm aware of in the world in Xinjiang, China. And this is deployed at scale using, as you can see, solar as the electricity generation. 1 gigawatt hour is really demonstrating that this technology can be scaled up to grid scale. And also, if you think about the manufacturing issue, you'd be familiar with the idea of a gigafactory for lithium-ion batteries. Well, again, in Zhuhai in China, there are examples where, again, you can make these things in an automated manner, and so reducing the cost of manufacture. And I think more maybe pertinent to the audience, we have something a bit closer to home in Europe. We have an example of a new project out in Switzerland, where at least by today's numbers, will be the largest flow battery in the world, once completed, a 2.1 gigawatt hour vanadium flow battery. And I believe this would essentially be able to provide electricity roughly for about 200,000 homes for a day, just to give you a sense of the scale. So this technology is deployed, but nonetheless still has challenges to overcome. What are the key areas of research at the single cell level? Well, there's different things that people look at. So electrolytes is one, whether it's aqueous or non-aqueous, hybrid systems with plating on one side, for example, slurry systems, semi-solid ones, and solar. This is often to do with playing at different voltages and having an impact on the accessible power densities or indeed energy densities. People are also researching a range of different anion exchange membranes, cation exchange membranes, indeed membranes that have an aspect of both. This is research that's ongoing, but also often borrows from other electrochemical devices. Electrodes are also in the crosshairs because, of course, this is where the electrochemical reactions happen. This is where the electron transfer takes place. There's a lot of work to look at improving those processes, making the reactions occur more electrochemically reversibly, but also producing these maybe from biomass, maybe from different manufacturing techniques such as electrospinning. And there's also maybe less, but still some research as well that's looking at how do we get a nice uniform distribution of our liquids as we flow them into those cavities, as I explained earlier. So you can just see here the different kind of concentration fields across different geometries of cell design. So then what do we actually research here at QUB amongst all of that global research? Well, we have published in the space of electrolytes. We have been very interested for the last few years in all soluble, all ion electrolytes. Again, here this goes back to the price volatility of vanadium and the much larger abundance and availability of ion systems. So that's been an interesting area for us for some years now. We also do some work in membranes. We look at crossover and try to understand how to minimize crossover, which correlates with self-discharge. There are some PhD students here that are actively working on activating electrodes, so using traditional felt electrodes, but in this case, decorating with, for example, polyoxymetalates to improve electrochemical performance. And we've also published, and most relevant to the work that we're presenting today, some work in cell design, whereby during Hugh's PhD, he developed a 3D printing platform to produce those flow frames I mentioned before. So this is the structure that allows us to control the flow in and out and indeed distribute it across that electrode cavity. This has been key enabling technology for what we are presenting today. So that brings me to what does our setup look like in our lab? So this is a render of our system. So you can see here we have our cell, our 3D printed cell I just mentioned in the middle. We have our electrolyte reservoir tanks. We have a peristaltic pump tubing. We also have inert gas to keep the vanadium system free from aerial oxidation. And we have our electrical connections. And this is a very, very standard setup. All of these may look slightly different from different labs, but this is a setup that Hugh kind of helped with, well, was pioneering during his PhD, because it's very expensive to buy commercial cells. This is a way that we can produce them with design versatility, but also at low cost. So where this work has kind of sprung from was originally quite early on. We noticed something when we were essentially performing nominally identical experiments. And we would actually put our current and voltage traces on top of one another. So this is a very standard electrochemical technique in flow batteries, indeed in many batteries. You're charging up to a point and discharging, and you're repeating that. So you're charge, discharge, cycling. And what we notice, if you put 3 repeats of nominally the same experiment on top of each other, before long, only at cycle 10, you've got quite a disparity in the results. And what this meant was that we're obviously not controlling for as many variables as we thought when we're repeating our experiments. And indeed, when we looked at the literature, we could see that the flow battery field was really taking off over the last 15 years, but certainly it's more in those areas I presented earlier. So it might be the electrolyte, the electrode, the membrane, but certainly very, very little in testing protocols. And if you go deeper, this was some work carried out by Hugh and Alex, where they looked at the most highly cited papers across the last sort of 25 years or so. And there are some really key bits of data that were always included, and some what you might imagine might be useful data to know that was always excluded. And most importantly, if we look at this final column, so replicates, how many times did people present n equals 2 or above? Across these cited pieces of work, it was 0. So this was quite a surprise for us, but it also meant that we were onto something. This is something that needs to be studied further. So in our labs with our 3D printed cell, what we set about doing was actually looking at how variable are our systems and how might we go about mitigating that variability. So what we're presenting here, which is from our paper last year, is the baseline repeatability of our 3D printed setup. And that is to say that when we're taking charge-discharge as our electrochemical technique of interest, what you can look at is Coulombic efficiency, so how much of your charge that you put in are you getting back out, your voltage efficiency, so how efficiently are you using the energy, how many polarization losses are you experiencing in your charge-discharge, the product of the two, and then electrolyte utilization, how much of the capacity that you theoretically have there from the electrolyte you've chosen are you actually accessing. And what you see here is, without making any refinements, we've got not insignificant amounts of, so well, this standard deviation up to about 4 here, certainly 1, 2, 3%. It's not negligible. And in this work, what we looked at is what could we do to try to reduce those repeatability errors. And amongst many different things that we investigated, the ones that we found to have pertinence, that they really did actually impact on that variability, were to be very careful with how you calibrated your pumps and defined your flow rate. So you can see in these different metrics compared to the baseline here in yellow, these dropping as we go. And this was done in a kind of one factor at a time approach. And you can see that we further improved it by getting the correct fitment of our electrode within our electrode cavity, and then looking at membrane treatment or how pristine or treated or reused the membrane was. Again, we managed to bring down our variability by over an order of magnitude. Outcomes of that work, but the references here, what we were able to do is at least provide some guidelines. These are some ideas of things that not only should we be looking at, but we should be giving detail on when we're publishing. These are elements that may be accounting for the variability that at least we were experiencing with our cell. So this is all well and good. This is what we were doing in our own lab, but of course our system is not necessarily the same as every other system. One stage we, at the beginning of 2024, Hugh was over in Queen Mary University actually presenting some other work about computational experiments, but was chatting with some of the people there about what their experiences were. And it turns out that a lot of other flow battery researchers, perhaps even all the ones he spoke to, had very similar experiences of the lack of repeatability in their own tests, but also the inability to replicate what they were seeing in the literature. And this was very timely because I think towards the end of that conference, there was a very candid talk given by a professor at MIT. So this is Professor Ficquelet-Bruchette, where he was being very honest about the fact that in their labs, they were also struggling to reproduce what they were seeing in the literature. And certainly he had a keenness to maybe start looking as a community at some of these issues. How could we come together to investigate and potentially mitigate these sources of error? And what that led to, once we realized there was a critical mass of people that were interested in this, was the beginning of our multi-institutional studies. So what we are terming phase one. So what did our phase one look like? Well, it was led by MIT in Queens, but we were also lucky to have on board researchers from Queen Mary, Cambridge, Manchester, Eindhoven, and Harvard, 8 research groups from 7 institutions. And the way we set about it was that we sent out a questionnaire to everybody to understand what capabilities and capacity they had for this type of testing. In the meantime, the 2 lead organizations set about figuring out, with the equipment we have, what are suitable tests, where just sort of sanity checking the sorts of things we might want to ask the participants to undertake in such a multi-institutional study. And so what I'd like to try to do is summarize a year's worth of endeavor around this phase one with this lovely figure that Hugh produced for the paper that we have recently had published in Energy and Environmental Science. And what this does is show you across the year of 2024 that we started off with those conversations at Queen Mary, through our own and through Professor Bruchette's network, put together this network of flow battery researchers who confirmed they wanted to take part. We began some of our own testing. We set up communication channels so that we could correspond with each of the individuals. As I mentioned, presented a survey to understand capacity and started manufacturing cells. What we didn't realize was our cells were very robust for our own labs, but once you send them, and once they're in transit, you actually have some problems with their stability. So we had to redesign our nozzles to make them more robust for couriers. And then when everybody had the cell, we worked together as a lead group to basically come up with an experimental ask for all the participants to follow. That testing was done towards the end of that year and then sent in, anonymized, analyzed, and this then led to the analysis and manuscript writing. And what I want to do is just spend a little bit of time explaining what we asked participants and then talking a little bit about the data and the analysis that came about from that. So those of you familiar with flow batteries, you'll be familiar. Normally you have 2 different electrolytes, or at least the vanadium system would have +5, +4, and +3, +2. In this case, we didn't want to have any specific issues with crossover between 2 different electrolytes. We kept the system very simple. So we asked our participants to perform a symmetrical cell test, and we specified that we want to look at ferricyanide because we know it's a well-studied, stable electrochemical redox couple. And in particular, we provided all these components, whether it's electrodes or membranes. We asked our participants to buy the chemicals so that we weren't sending those. And then we provided all of the kit for them to put together their cells, and we asked for a polarization curve, impedance investigation, and charge discharge cycling. Now, if you're familiar with flow batteries, those will be reasonably familiar electrochemical techniques. For those that are less familiar, polarization curve analysis is essentially applying pulses of increasing current density and examining the potential response or vice versa. And essentially what it allows you to do is at least qualitatively see if you're at the low current densities, you get to probe the activation losses, and the intermediate ones, the ohmic losses, and then at the high current densities, you're really probing mass transport losses. And you can do this more quantitatively, and you can get a little bit more information by applying impedance spectroscopy, which is shown here in B, and then C and D correspond to charge discharge cycling. So this is, in this case, galvanostatic, holding a constant current, and charging between an upper voltage cutoff and a lower voltage cutoff. And of course, we can look at how well is capacity retained during that charge discharge cycling. And so one of the questions when we're presenting this study has always been, what have you fixed and what have you allowed the participants to change? So it's important here in phase 1 that we fixed the electrolyte chemistry, as mentioned, this 0.2 mole of ferrocyanide. We fixed the electrochemical cells, so we did lots of cell production here at Queen's University Belfast and sent it off to the different institutions. We provided a cell assembly guide and even a video, and we specified the flow rates. We specified those 3 electrochemical techniques, and then within those techniques, we provided some clear parameters. What we didn't fix were things like the chemical purity of the chemicals that were bought, the auxiliary systems, the pumps, tanks, tubing connections, exactly how people treated their electrodes and electrolytes, the order of their techniques, and indeed within those electrochemical techniques, some of the protocols that could be used. For example, I'll get to this now in one of the coming slides, exactly how long are those pulses that I mentioned, and what's the difference between one pulse and the next in terms of the current applied. And this is just, again, I won't go into the detail. You can find this in the Energy and Environmental Science paper. But we were really surprised by just how much variability there still was, despite controlling for quite a lot of it. So, for example, how people connected to their cell and with what type of connectors, to how, whether they mixed or not, whether they sparged their electrolyte, how they cut or measured out and cut their electrodes. So there's a huge amount of variability that we managed to capture as metadata in this study. But I'd like now, the next few slides, to just actually make some comments on the data that we got back from the study. And before I dive into that, the other kind of surprise from this work was actually that the polarization curve that I mentioned, that is somewhat standardized in other electrochemical techniques, turns out to be a little less standardized in the flow battery arena, at least across the 7 institutions, 8 research groups that were working on this. And what we noticed, and what I'm showing here, is for each of the participants, we have their voltage trace and current density trace. And what we are seeing is 8 different approaches to exactly the same type of electrochemical technique. So not a single repeated protocol across the 8 different research groups. So that was very telling for us that this is something potentially that needs to be tightened, that a protocol or best practices or some sort of guidelines might be useful. Because after all, when we go to a literature and we see the output, those polarization curves that we're seeing, often the information behind it isn't there. So we may be not comparing apples with apples. Notwithstanding that the protocols were done slightly differently, we can also look at the polarization data itself. So this is the cell potential for the positive polarization. You can see there's variability across these different groups as you go up in current density, how the cell potential is reacting. And we were able to do some basic statistical analysis on the mean and the coefficient of variation. And what we see is even when we correct for some of the differences in the ohmic losses, okay, some of them collapse together, but you still have at least 3 or 4 outliers. And we certainly see much more greater variation at the lower current densities. So we have now a quantifiable understanding of the variability across these different institutions for polarization analysis, which unfortunately is a convolution between the different cells and assembly the way the technique is being applied. What I'm showing here now will be familiar to flow battery research as well, which is we also asked the participants to do impedance spectroscopy. And impedance spectroscopy is applying an AC current and monitoring an AC voltage or vice versa. And essentially what comes from that is that you're able to get information on impedance, which is the umbrella term for resistance, capacitance, and inductance. And if it's plotted as the real part of the impedance to the negative of the imaginary part of the impedance, you get something called a Nyquist plot. And you can see that all those 8 different participants have very different shapes and sizes of their responses. And what we're able to do is apply the same equivalent circuit model, which is essentially a way of modeling what does this imply for the electrochemical system. And we were able to quantify their ohmic, charge transport, and mass transport losses. And we saw some trends that we expected to go up in flow rate and you lower the mass transport. But what we weren't expecting is such large variability in the ohmic loss. Even though everyone was using the same cell and in principle assembling them following the same instructions and compressing to the same torque value, we still had quite a degree of variation in ohmic loss. And finally, charge discharge cycling, the most common electrochemical technique in flow batteries. You can see again, this is the spread across those 8 different institutions, or 8 different research groups, I should say. And even when it's IR corrected, they do not collapse. And what we're able to see is there is significant variability in the OH potentials. So how much loss in the system as we're charging and discharging really still varies despite using the same cell. And as I mentioned, doesn't collapse if we correct for the IR loss. And what we're able to do is quantify and then look at the order of that replicability error. So capacity decay was the most variable, followed by electrolyte utilization, followed by voltage efficiency, and then the Coulombic efficiency, which is essentially looking at things like crossover and side interactions. This seemed to be the least variable across the systems. For the interest of time, I'm just going to skip through a couple of slides here. This is looking at correlations across techniques. But if you'd like to read a bit more about the correlations between those techniques, I point you towards the Energy Environmental Science paper. What I would like to do is touch upon those, trying to link some of the variable practices to the issues that we've seen. So we tried to investigate, once we had all this data and metadata, what type of things do we think are most dominant causes of that replicability error? And one of the things we looked at was electrical connections. We saw that actually up to about 25% of the median area-specific resistance might derive from those poor connections. And we also looked at potential for electrolyte bypass. So essentially we looked at stirring or not stirring, where the inlet and outlet tubes are. And if you look, for example, at this configuration, if your tubes are a bit too close and you're not stirring, we can have this huge precipitous drop in electrolyte utilization. And that's not to say that was what's happening in our systems, but it just goes to show that if there is an element of bypass that's occurring, this can have quite an impact and might be leading to that variability in electrolyte utilization. The important thing to note, though, is that n equals 8 with 8 different data sets, it was very difficult to unambiguously ascribe certain practices to greater variability. So we presented this work at a variety of conferences. We were very pleasantly surprised. Everyone was very interested. They were suffering from the same issues. And lots of researchers then signed up. So from universities, national laboratories, even a couple of companies, they signed up to what we're now working on, which we call phase 2. At that point, we sort of started planning, what is phase 2 going to look like versus phase 1? What should we refine? Can we also inspect something that we're terming reproducibility, which here we define repeatability as being in the same lab, repeat the same experiment, replicability with the same cell but in different institutions, whereas reproducibility is asking the same question using your own equipment that you normally use and seeing what the variability is as you perform those experiments. And so just to give you a bit of a sort of zoom out, our phase 1 was 8 researchers with kit provided by us, and that's been published, the DOI is there. And phase 2, we split it between phase 2A and phase 2B. Now we've risen to about 38 to 41 researchers. In phase 2A, the different researchers, first of all, perform the same experiments, but with their own cells. And we've collected all this data and we presented this at the UK Flow Battery Network Symposium earlier this year. And at phase 2B, we're still collecting some of the data sets, but this is actually using a refined style. You can see here a render of a sort of improvements that have come out of the phase 1 work that I've just been presenting. This was sent out to all of the researchers so that we can further understand replicability, but with n equals more like 40 rather than n equals 8. And this slide is just to sort of show the breadth of the institutions that are involved. So we have not just people from the UK, but also from North America, lots from Europe, and some from Australia as well. So we have 33 institutions, 41 researchers, and about 38 data sets. So this really brings me now, sets the stage for why do we need data infrastructure, and why did we apply for funding, and why did we run a project with the PSDI? Well, there was 3 main different motivating cases for data infrastructure. One is with n equals 8, it was something the leading institutions could handle manually, but with the sheer size of the data sets individually and the number of them, we wanted to move to a much more sort of automated analysis schedule. Indeed, we also wanted to not necessarily concentrate that analysis just to a few members of the growing consortium. So instead, we want to decentralize analysis, have tools that people could use without relying on all working together in the same institution, or indeed just being the lead organizers. And finally, and I think most importantly to us, we wanted to generate tools that were useful for the community, but could have longevity and legacy, so that these tools could, in principle, be used by researchers that are not involved in our studies, that the tools are available in such a way that people could carry out their own tests, upload their own data, and compare themselves to the community data that was available. So during the project, we set about thinking about this as a data pipeline. So at the beginning of that pipeline is the experimental data that comes out of the different potentiostat software that people are using. And we need to collect that data, but we also need to collect the metadata alongside it. And then we need to ingest that data and store it in a curated manner that we can then both share in terms of the metadata, that's I'll get to in a moment, is shared on the community data collections as PSDI resource, but also to visualize it. So we have the metadata and visualization tool that's built in Marimo with Python, which I think Hugh will be demonstrating a little bit further on in today's presentation. So some of the thought process behind the way that we went about this data infrastructure, so it's just a couple of plots. So this is looking across the phase 2A participants, which potentiostats are used. We can see Biologica by far the most popular potentiostat brand. But also from looking through our original requests for data, we noticed that we can specify as much as we like how we'd like data to come in. People are extremely busy. There's also different interpretations. You're never going to end up with completely error-free submissions. And what we found is that almost half had some level of error involved if we provided quite a loose protocol for data submission. So the decision that came from these and a few other bits of data were to use familiar software, provide a very rigid template, and provide granular guidance, particularly aimed at biologic users, that embedded calculations of the data that they were putting into the data entry template for quality control. And then to use some Python behind the scenes, not rely on chemists or chemical engineers necessarily to be au fait with writing Python scripts, but use those instead behind the scenes to ingest all of the information and place it into a database. And so here's a little bit of information about that. So this is our data collection ingestion data entry template. So you can see here we have a user guide page. So this is how to import the data specifically from the biology EC lab software. This can be followed through to make sure that the data is exported in the same way in every case. Once it's imported, you can put them manually, you can put the data in here. You can also put in your flow rate, your active area. It's automatically indexed, so it knows whether it's a charge or a discharge first step, which cycle it is, what step time it is. And essentially this allows for very rudimentary error checking right from the get-go, because this should all correspond very simply to what you would expect from the data that you're pasting in. Importantly, there's also some user adjustable filters. That means that you can also exclude certain cycles. So for example, the first cycle that you might want not to include some of the information from the first or maybe last cycle, you can use user adjustable filters to filter those out. This allows you to screen as well. You can see that it automatically changes if there's some error that is expected. And we also calculate the average and variance across the 3 repeats that we've asked from our participants. And so that gives us the data, but we also, as I mentioned, need the metadata. So we looked at ingesting this a number of ways. And actually, again, we looked for the most accessible. So we were working with spreadsheets. We thought, well, let's try Microsoft Forms. And in the first instance, and this was a real learning curve for us, in phase 2A, we had quite an unstructured questionnaire with very free-form answers. Many questions at this stage, or we thought were quite numerous. We were asking about personal information, componentry, how they set up cells, how participants prepared their electrolyte. But what we realize is that with that setup, it's very, very difficult to then curate that data and display that in a way that doesn't give you completely unique responses for every single different participant. And so by phase 2B, we had, okay, we're still using Microsoft Forms. We also wanted to share the data. So the community data collection, which is available on the PSDI website once it's back up, is a way of sharing that metadata on a Zenodo-like platform and Venio RDM platform. But we structured our questionnaire in such a way that we gave multiple choice answers. In fact, we increased our questions twofold, and all of this allows us to populate the CDC and also populate our own SQL database with much more consistent and rigorous metadata And actually we expanded to include information about how electrodes and membranes were stored, pre-treatments and things like this. So this was a real learning curve for us in terms of how to request and then how to deal with metadata. And this is just a slide to show a little bit behind the scenes. We have multiple SQL databases. We store electrochemical data in one, the experimental metadata in another. The code is then scheduled to run every hour to search through and ingest any new data that's in. So this is a good pipeline actually. So this is the entry template, it goes onto the Google Drive. We check it. Once we're happy and it's clean, it goes onto a specific folder. This code then passes any changes and that's ingested in the SQL database. And at the moment, just to give you a sense, we're dealing with about, from the clean data that we've worked with, about 12 million total data rows. So we haven't got a chance to actually go and browse, but we've got a screenshot here. So this is what the PSDI resource theme looks like. So it's called Open Source Repositories for Flow Battery Data. Our data source, this will take you to the community data collection, which is where we store our experimental metadata. And we also have this service, which is the data dashboard, which I believe we can demonstrate in a couple of minutes. Hugh will do a live demonstration. Hopefully everything goes nice and smoothly. And this is just a screenshot of that flow battery experimental metadata repository. This is the community data collection, which is housed on the PSDI site. They have plenty more of these that are really well populated and provide lots of great data. In our case, we've got at the moment the clean phase 2B metadata participants. So you can go there and you can see how has all of these different participants actually set up their experiments. I think at this point, I'm going to ask Hugh to share his screen and demonstrate the dashboard.
Thanks, Josh. So yeah, as Josh said, live demos, a bit risky, but we'll see how it goes. So this is the sort of data dashboard that we came up with. I just realized that we didn't put the link in the actual presentation, but it's publicly accessible at flowbatterydata.org, if Josh might pop in the chat there. So there's kind of a little summary at the start of the project that Josh has covered really nicely. But we'll start off with some overall summary statistics. So you can just see like the total number of data sets, the total number of data rows when data was last ingested, for example. And as far as we know, this is the largest publicly available flow battery data set out there at the minute, certainly for repeat data, which is kind of cool. If somebody knows of a bigger one, let us know and I'll amend that claim as far as I can tell. And then we also have summary statistics for all of the different phases. So phase 2A, where participants use their own cells, and phase 2B, where they used the cell we sent out. So there's some really interesting sites, even before we get into data, like top level data. So we get to see what type of cells different groups use and what like the actual structure of the cell themselves. And then, yeah, like for example, you see this huge variation in the type of electrodes that different groups are using. So it was really interesting before we even get into data to see what people are actually doing. And then, yeah, different cell areas as well. As Josh mentioned, with our really in-depth questionnaire for phase 2B, we're able to collect a huge amount of metadata. And again, really interesting how differently people work in their labs. So even things like how they cut their electrodes and how they connect to their cell, there's basically no consensus. I guess this project's trying to aim to see how much of an effect those things actually have. So I'll quickly show you some of the things that the dashboard can do when you're actually looking at the experimental data that was submitted. So if you wanted to, if you were crazy, you could look at all of the data sets at once. So here's all of the phase 2B data, for example, but it probably gets more useful when we start to look at individual participants. So I've chosen a couple to chat about today. So like P44, for example, here there are 3 repeats of the same cycling test. And it's really cool to be able to compare. So you can see that within their data set, they're quite repeatable, right? Those charge-discharge curves are largely on top of each other. But we can compare them to other groups. So here's P45, which is a particularly nice data set. They were able to get exactly the same data 3 times in a row. So they were super repeatable. And we can start to probe like, oh, what did P44, P45 do differently, so that we can try and learn from these different data sets. And we can also put the different phases on top of each other as well, which can be quite interesting. So the blue and the purple there, they're slightly different cells, so you'd expect them to be different. And then the green and the yellow here, they're both using the same cells, so they're largely the same, right? That's kind of cool to see them grouped together. And I'm just realizing when we put one repeat on, so then again, you can look at the different repeats for the different phases of the study. And then perhaps the most powerful part about this is that you can see this data in context. So you can see the data and then actually how they generated it. So all of the metadata practices, at least for phase 2B anyway, we're still working out how to reformat the phase 2A data. And then we tried to take as much information as we could. So for example, looking at people's experience. So there may be a correlation with how long you've worked with flow batteries and how repeatable your data is. So yeah, it'd be really cool to see what comes out in the wash there. Where we're running a little bit behind, so I'll fly through quickly. With the same participants, we can then look at the metrics that are calculated from their testing. So yeah, you can see for the P45 again is super repeatable. So I'll look at, for example, discharge capacity. These are two different cells, so the discharge capacities are very different, but we did our best to normalize the data. So whenever we look at electrolyte utilization instead of the actual discharge capacity, so we normalize it for the amount of electrolyte in the tanks, you can see that they kind of start to converge again a bit. And then, yeah, we mentioned in our single lab study, capacity decay had the biggest variation, and even using this symmetrical cell, it was quite noticeable. Another way we can look at the different participants' data is instead of looking at per cycle metrics, we can look at the overall average metrics. And really quickly, this lets us see where certain participants were really good at getting the same results over and over again, right? So for example, P45 is particularly good at getting the same coulombic efficiency over and over again, but P44 struggled when using our new cell that we sent out. This pattern is kind of, it changes slightly for different metrics, but it's really interesting that you can quickly see where people's testing methods led to really nice data and where they could be improved. And then there's a heat map to actually quickly highlight where particular participants were really good or really bad at getting a particular metric. I'll spend another couple of minutes looking at P44 and P45, so polarization curve analysis, for example. I think Josh is going to go through these in a bit more detail. But yeah, with the different cells, again, you can see really quickly that we can pick out these different characteristics. And then there's some like polarization particular metadata and then other metadata as well. So you can look at it in context. And then lastly, EIS. So we've just got the Nyquist plots on here currently. We'll look at all of the P44 and P45 data, and the kind of the pattern that we've seen throughout with these two data sets is that P45 was particularly good at getting the same data again. And yeah, it's always nice to kind of remind us that, so for example, both of these 2B data sets should be nominally the same data, so we'd like to see them right on top of each other, but there are still quite appreciable differences between them. So we do have some way to go on our testing. I hope that sort of shows off some of the capabilities that this dashboard can do. If you're interested, I highly recommend you go and have a poke about at flowbatterydata.org. I think at that, I'll hand it back to you, Josh.
Thank you for the demonstration, Hugh. There's just some screenshots looking at some selected data just to give a little bit more insight into what we're able to look at. So Hugh showed there the polarization data and what we have from phase 2A, 10 selected participants using similar active area, 5 centimeters squared, slightly different cells. But then also polarization data from phase 2B using our same cell, slightly different active area, but normalized for the current density. And you can start to see those differences between replicability error. This is where people using the same cell, but their own auxiliaries, versus actually using different cells as well as different auxiliaries, a reproducibility error that I was alluding to before as well. And in impedance, we see something similar. So here from phase 2A, we have quite a spread from very, very low impedance to much higher compared to our kind of interim but much more clustered situation with 10 selected participants using the same cell. And the case is kind of borne out as well in charge discharge cycling, but again, this is just a select sample of the number of participants. There's a lot of metadata behind some of these things, whether or not the variability in the actual distribution we can look at, as well as comparing that to where they stand in terms of replicability or reproducibility. So that's just sort of showing the level of granular data, but also study-wide statistics that we can start looking at. And I just wanted to reiterate what Hugh said there. We've got a huge amount of metadata. That's all that from the phase 2B is currently on the dashboard, and phase 2A we're working to upload. But this, in principle, allows us to start linking in a way that we found very, very challenging to do with n=8, the differences, the error sources, the different approaches, the different parameters to the outcomes, the electrochemical performance data and metrics that we're interested in. So that gives a summary to the data infrastructure. I know we're sort of short on time. We want to leave some time for questions, but I'll just use the last few minutes to talk about a community workshop. The PSDI very kindly supported a international QUB PSDI flow battery reproducibility workshop held at the end of March. We got sponsorship from themselves and also SciMed and the RSC Service Catalyst Interest Group. And a big shout out to the Digital Curation Centre for helping us put this on. And we actually welcomed 27 participants from 23 institutions in person and many more online. And we held it in Belfast. This is just to show how close everything was. And it was really a chance to celebrate, to reflect on the study, get feedbacks on the data infrastructure, and also think about the next steps. And so here's just some photos. The first day we did some lecture-style talks. I had lots of people asking questions of our industrial speakers, our sponsor, ourselves, and also both the PSDI and the DCC. I did some intro talks. And the second session held in our graduate school, we really kind of came together in classroom-style sessions to really ask what's gone well and what could we be doing better. And it's really now started conversations about phase 3 and also how to make the most of the phase 2 data and metadata. So to conclude, I hope I've shown that single-cell lab testing can be improved if you follow strict protocols, that multi-institution testing can be used to quantify replicability errors. N equals 8 participants is certainly not sufficient to unequivocally attribute errors, but that we have been able to show that cell electrical connections, electrolyte bypass definitely contribute to some extent. But if you have N is greater than 30 participant level data, you need data infrastructure to really facilitate the analysis of it and also enable the community to be involved. Importantly, this is not finished work, this is ongoing. We want to collect the remaining phase 2b data and ingest the phase 2a metadata. We want to improve our data infrastructure, so designing a new data import tool, more automation, adding new features. And certainly we've got so much data now, we're considering some AI tool integration to really kind of pinpoint the error sources. We're writing manuscripts, we're applying for a cost action grant together as a community, and we're also in conversation with National Physical Laboratory to run a user variability study. This is where everyone uses the same potential state electrochemical protocol, cell and otherwise, to really just look at the variation derived from the participant. And with that, I'd just like to thank everybody who's come today to listen to us talk about our work. Particularly a big thank you to Hugh as the postdoc on the 6-month PSDI project, the PSDI and all the names there for all of their help facilitating this work and the workshop. Especially also the DCC, so Linda, Agnes, and Carolina for their help. The study leads, Alex, Thomas, Adon, and Fick. Daniel, Janssen, and Michael here at QUB for helping with distributing the cells. Christian Stolzer for help with data, and all the participants that have taken the data. And I would, with that, just like to thank you again and open the floor to questions.
Thank you, Josh. Thank you, Hugh. Really wonderful presentation, and I'm glad that the live demo went well. Let's now open the floor for questions. You mentioned that different groups approach experiments in different ways. Do you think it will be hard for you or all as a community to agree on a best practice?
That's a great question. One of the things we've been focused on in the first phase was measuring the difference. And in the second phase, trying to understand what the sources, which are the most dominant sources of error are actually having an impact on the performance. The kind of next step and the step that we're starting to think about now is how do you get standards adopted? So how do you work with the community to come to a consensus around community standards? And we're approaching it in a few ways. One way is that we have a community much larger than just these multi-institutional studies. So we have a Discord server, Flow Battery Commons it's called. So we're actually dealing with sort of 80, 90 researchers who can discuss these things and hopefully come to a consensus. We're also really keen at bringing people together. So that workshop was fantastic for that. We could actually say, we could devote time where we're actually trying to work towards consensus, and it's not just the study leads that are making those decisions. And certainly one of the things that we're interested in is applying for further funding to make this a larger effort, so that we can then devote more time to bringing people together and writing these guidelines together, because it's a really great question. You've got to have consensus and you can't be too strict. But if we can show with data how much it improves things, the hope is that people will want to do it because the data is there to support it.
Thank you. Another question. How did the second version of the metadata collection questionnaire work out? Do you see any way to further improve that, for example, capturing those metadata real time?
That's also an excellent question. So it worked out a lot better in the sense that we were able to capture it in a way that could then be ingested, displayed, and viewed by the community in a way that it was too cumbersome with phase 2A. What the questionnaire really, I think, is starting to touch on there is there is a step between what is happening and the participant then reporting what is happening. And if you can kind of reduce that gap or completely remove that gap, then you might have even more reliable metadata. So one of the things that I'm very interested in, sort of on the Internet of Things level, is could we be collecting some of this metadata live alongside the electrochemical data? For example, let's say that the temperature is just being collected live. It could be something to do with the humidity in the room. It could be that you've even got flow meters that are actually giving you information about the flow. We're a little bit away from that. The resource needs to, we need to grow this, but we'll be putting in applications to try to move towards that, because we think that yes, the strength of our metadata will increase if we can actually get some of that live feedback.
I have another comment. Very nice presentation. I wish this data sharing policy was also followed in electrode materials and manufacturing in lithium-ion batteries.
Yeah, no, it's interesting. My first foray into multi-institutional studies was actually in lithium-ion batteries. So when I was a postdoc working on a Faraday Institution project at University College London, the Nextrode project, one of the Faraday Institution's attempts, I think, to make sort of thicker electrodes. One of its work packages that I was working on was a round robin study. And it was looking at coin cells and how they're put together and how they are tested. I'm not sure where that got to. I unfortunately left UCL soon after that. It's a very difficult endeavor, and like the flow battery systems, there are complex systems with lots of different elements involved. But from what I remember from that, there was quite a degree of variability, even with nominally the same cell materials, same amount of electrolyte, same coin cell sizes, and how they were compressed. So yes, we are in agreement that the flow batteries are not the only field that can benefit from this. And what we're very interested to do, especially with our cost action at European level, is start to understand which other areas could benefit from some of the tools that we're developing.
Cool. I think that's all the questions we have. And thank you very much. This is our PSDI website. You can see all the resources we are providing. If you go to this links, you can see the resources and data pages Josh mentioned in today's talk. We have a couple of events upcoming. As I mentioned earlier, this is part of our webinar series. So the next event in the series is on July 9th. The registration links are open now. You can see them on our events page. We have also a workshop coming next month, that is 16th of July, transitioning from FAIR to AI ready data. It's an in-person event here in Southampton University, so please join us. And we are on all the social media platforms. You can search us using the keyword PSDI. All our previous webinars are available on our YouTube channel. Please take a look at them. Being said that, thank you again for joining us today. Thank you for the speakers for giving us a wonderful talk, and see you in the next webinar.